All right, good morning, everyone. We're going to finish our classwork problems from yesterday. So we're going to finish 6.3. We have 2 more problems that we didn't get to. We'll finish those, and then we can move on to 6.2, which is solving differential equations for 6.2. But I think you're going to find it to be a lot easier. We just have to deal with basically just using an equation and solving the equation one variable at a time. So yeah, not difficult, just have to be careful with keeping track of our values or keeping track of our steps. Okay, but first, we're going to get some more practice in with differential equations before we move on to our word problems from 6.2. Okay, so it says find a general solution to y prime equals 6 cosine of pi x. I'll write this a little bit larger here. All right, so first things first, what can we do to rewrite this problem? Yeah, let's get that y prime to be more descriptive for us. Let's get that dy dx to show up. And I'm already foreseeing the need for cross multiplying, so I'm just going to put this in the fraction form here. Okay, we're going to go ahead and cross multiply. Again, I like to cross multiply, not because it's going to guarantee a separation of variables, but it will make things a little cleaner to look at, not having to look at any denominator here. So y dy y dy equals 6 cosine pi x dx. Do we have full separation of variables? Okay, so we already have it. No need to move anything. Dy and dx are in the right positions. Y and x, they don't have to be in the numerator, but it just so happens that they're there, so that's where they're supposed to be. Is there anything that I can do to clean up the left side? This is as bare minimum as I can make it, right? If there was a coefficient, then we can move to the right side, but this is as good as it's going to get. All right, so we're ready for our calculus step. We're going to take the antiderivative. And we're going to let's do the left side first, a little bit easier. What does integral of y become? Okay, y squared over 2. We just go through power rule. And the right side, I'm looking at this, and I think we can match a rule fairly quickly. But there's something we got to be careful about, and what's that? Okay, good. Yeah, we've got to take care. We've got to make sure we don't lose track of the 6. What else? Yeah, this is not just an x, right? There's a little bit of a u substitution going on. But I would like for us to get to the point where, for the easy u substitution, we can skip the step and just know what is going to be left over out of that process. So can you guys guess what's going to come out of that pi x after u substitution? Okay, something though, it's not quite just pi. Now derivative would be cosine of u would become negative sine of u times u prime. Yeah. Good. So that's just the slight adjustment we got to make. And once you're comfortable with that, understanding that you're just taking the reciprocal of the derivative, then you can save a lot of time, especially for the easier u substitution linear problems. But for now, I'm going to show all the steps for u substitution until you feel comfortable to make that jump. So I'm going to let the we'll let the u value be pi x. du over dx equals pi. Make that substitution here. So pi x becomes u, dx becomes du over pi. We keep track of that 6. That pi comes out as a denominator, so 6 times 1 over pi, integral of cosine of u du. Okay, and then so we know that this cleans up to be 6 over pi. Integral of cosine is sine of u, and then replace the u back in terms of x. So this whole thing is just going to be 6 over pi sine of pi x plus c. So you can go through all this and arrive at the right answer, which is perfect, which is fine. But if we can save a little bit of time, that will be even better, right? So if you can understand that, all right, I know what rule I'm trying to pair up with, cosine has become sine, but I know there's something little extra that's going to come from that pi x. The derivative of pi x is just pi. Take the reciprocal, that's 1 over pi, and that's just going to go right here. And if you can make that jump, then you can just basically follow the rule. Cosine of u becomes sine of u plus c, and I'm just taking care of that pi out in front here. We can save, a little bit of time that way, which means that you can do that for any linear coefficients, right? If it's 3/4 x, you can just push that out as 4/3. If it's 1/3 x, you can push it out as 3. If it's 5x, you can push it out as 1/5. Right? So if you can make that jump, save a little bit of time that way. Okay, any questions up to this point? Okay, this problem is asking for a particular solution, but I just want to tell you that if you can get to this point, right, you have a very, it's incomplete, but it is a variation of a solution, okay? And because of that, because of the fact that you've kind of already gotten to a version of the answer, the majority of the points you've already earned, right? So if you can separate the variables, if you can find the antiderivative, get that plus c to show up, you've already earned the majority of credits. Now, it is true that the rest of it is easy to make mistakes because there's so many other things you got to keep track of, and sometimes it's algebraic mistakes can happen. But the good news is that it's minimal in terms of the points. So if you can get to this point, you've earned the majority of points on the test as well as on the AP exam. On the AP exam, anything past this is very minimal, like maybe 1, maybe 2 points, but really you've shown your knowledge of your calculus up to this point already. Okay, the rest is just algebraic stuff, which on the AP exam as well, they are definitely de-emphasizing the algebraic parts and emphasizing the setup and the calculus knowledge. All right, so I'm going to bring this up to the top here so we can kind of have a restart here. And I know I'm trying to get my way down to a y. I know that I eventually have to decide whether I want to solve for c now or solve for c later. But I'm always looking at the left side going, if there's even a small little thing I can do to clean up, I'm going to go ahead and do that cleanup. That way I can kind of spread out the work over a series of steps rather than trying to do it all at once. So even if I see something small as moving a 2 over, I'm just going to do it. Just I know that's not going to resolve my y squared, but it'll just allow me to just take one step at a time. Distribute the 2 through. Okay, so I'm still sitting at an incomplete equation. This is a variation of the general solution, which I'm not going to get down to the very and I care more about just jumping directly to a particular solution. So I'm going to have to solve for C, and I'm going to have to solve for Y. But now the decision is, do we want to do that, solve for C now or solve for C later? And my logic is, or having done these problems, the pattern is I know that in the future a square root is going to come up. And if I can solve for C before the square root shows up, then I can minimize the messiness that can come from dealing with the square root. So if I foresee a square root in the future, like if I see y squared on the left, or y cubed, or y to the 3/2, any power of y where I got to deal with the root, I want to get to that C value before that root shows up. So that's what's guiding my decision here. Now, if you decide that you want to do a different way, it'll be a little messier, but you'll get the same answer. You won't get points taken off because you did a different way. That's just trying to share what I think is the cleanest, less messy way of working through this. So I'm going to go ahead and use my ordered pair to solve for C. So 1 goes in for X, 2 goes in for Y. Sine of pi is 0. 0 times anything is still 0. So my C is just equal to 4. Once I have my C value, I'm going to go back. Make sure that you are putting your C value back where you initially made your substitutions with your X and Y. Don't just pick a random equation with C in it and plug in for C, right? Because that may be a different point of the problem. So make sure you always go back to where you initially started that substitution and replace your C value there. Okay, so y squared is equal to 12 over pi. All right, so I solved for C, got that out of the way, and then when the square root comes along, I don't have to touch what's inside the square root anymore. All right, so square root. What's in front of the square root? Plus or minus, okay. Yeah, I want to keep reminding us of that as a reminder that there's two solutions, right? We gotta make a decision between two separate solutions here. Or y is equal to negative square root So how do we make a decision between our two possible solutions? Yeah, look at your ordered pair. Ultimately, we need the solution to hold that ordered pair. The ordered pair has to sit on one of these graphs, and a quick way to tell is we look at that y value. Whatever the sign of the y value is going to match the sign of your radical. So if because I have a positive 2, I want to choose a positive radical solution. If I have a negative 2, then I want to choose a negative square root. Okay, look at the sign of the y value. Okay, any questions here? All right, let's look at number 5. Number 5 says y prime is equal to x plus 1 times y. And then we'll put this over here, make it easier to read here. So we're going to just find the general solution. There's no order pairs here. All right, what do you see first? Yeah, that y prime. Okay, so y prime is dy dx. I'm going to just get my fractions set up for my next step. Cross multiply. So I like having everything in the numerator. Allows me to kind of get a clearer picture as to what is out of place or if there's anything I need to move. And what do you see? Right, there's only one thing out of place, right? Just have to divide that y over to the left side. Y's cancel out. Do I have full separation now? Okay. Y's together, X's together, we're good. But I will keep reminding us that it's okay to have a variable X or Y in the denominator if that's where it ends up. And I've seen enough of this where I'm going to keep saying it is, and I know as I've graded a lot of versions of student work here, a lot of students are uncomfortable seeing a variable X or Y in the denominator. And that's an issue because if we're uncomfortable with this, what I've seen in the past is students, they see this, they're not comfortable with where it is, and they want to move it to a location that is easier to work with. So they move it up to the numerator, and then they make it y dy is equal to the integral of x plus 1 dx, which can be the case for certain problems, but not for this problem. And the issue is, if you're starting at the wrong spot, then everything else is going to be messed up. It's not going to match with what we're looking for at the end. So we need to just be keep reminding ourselves that it's okay to have x's or y's in the denominator if that is where it ends up, right? As long as your dy and dx are sitting up top, it's okay to have your variable x or y in the denominator. We have rules that can handle that, so there's no need to move it if it's not where it belongs. All right, so we are ready for our integral rule. If you want, you can rewrite this. You can push that dy outside of the fraction if it makes it easier for you to match a rule. Okay, so what can we do with this 1 over y dy?
L and y.
Yeah. Matches perfectly. There's no need to go through u substitution if you're only making a one-letter substitution, right? This is basically, you can just jump directly to the rule and just make it natural log absolute value of y. Okay, what about the right side? Okay, just regular power rule. Good. Nothing complicated here. However, I do want to point out that maybe some of us are looking at the parentheses feeling like, oh, wait, does that mean there's u substitution? Because I see the parentheses there. Notice that the parentheses is basically, it's not doing anything, right? It's not, there's no coefficient in front, there's no exponent. So we can just rewrite this without the parentheses, and it's not going to change anything. Maybe it'll just make it clearer for us to see what steps necessary. So I want to just make you aware that the parentheses are good at the beginning to help us make sure that we don't mix up the parts that are not supposed to be together. But then we also don't want the parentheses to throw you off, right? At the end, we need to recognize that there's no need for u substitution here. We can drop the parentheses. There's no ugly exponent to resolve. There's no coefficient in front. These are just two separate terms. We can just use power rule. Okay, so x becomes x squared over 2. 1 becomes 1x. and then we need to include that plus C. Okay, questions here? Okay, so we have a version of the answer here, right? It's not quite cleaned up, but you've earned most of your points if you can get to this because you've separated the variables. You know how to separate the variables. You know you took the appropriate integral rule on both sides, and you've shown your knowledge of your calculus step. Right, the rest is just clean up. Okay, let's reset. I'll put this at the top. It says find a general solution. We want to solve for y. And okay, so before we do that, I know it's only asking for a general solution, but let's say this was asking for a specific solution. Okay, if it's asking for a specific solution, we know we got to solve for C, but I want to point out that typically, if I see natural log in the problem, I'm going to wait. I'm going to skip that y by itself and wait to the very end to solve for C, because the nice thing about natural log is that through the process of solving for y, that C is going to absorb, it's going to suck up a lot of the messiness around it, and it's going to clean up to be a fairly easy and nice equation. So I would rather wait until it gets nice and clean before I solve for the C value. If I solve for the C value at this point, I got to deal with a natural log. I got to hold on to that constant all the way through the process of solving for y, and it just makes for a messier process. So when I see natural log, and if I'm asked for a general solution, I'm going to wait, get that y by itself, get it all cleaned up, and then I have an easy equation at the end to solve for C. Okay, but it doesn't apply for this problem because we're just doing general solution. So we're going to jump directly to trying to get that y by itself. What can I do to resolve the messiness on the left side?
Put it to the E.
Yeah, so we know natural log. I want to undo that natural log, so I want to involve the inverse function. So I'm going to use this property. I know that e to the natural log of x is equal to x. So if I can raise both sides with e as the base, I can clean up the left side. And whatever I apply on one side of the equation, I'm going to balance that on the other side of the equation. Left side cleans up, e to the natural log just becomes absolute value of y. Now the right side, I want to try to isolate that c away from the rest of the expression. And we're going to take advantage of this exponential property. A to the m plus n can be expanded into a to the m times a to the n. So how can I use this to help me separate the c from the rest of the variables?
You could do like e to the x squared over 2 times e to the x times e to, or
okay, you're not wrong, but we can leave these two together.
Yeah.
Okay. I mean, you wouldn't be wrong if you did it your way. Just we can make it a little less complex. Okay, and then what? What comes after that?
e to the c.
Plus or times?
Times.
Times. Good. So times e to the c. That's something we got to be careful about. A plus in the exponent is not the same thing as plus between the terms. So that is something that we have to be careful about. A lot of mistakes are made here. Okay, so now plus c has now been converted into a times c because we know e to the c can be just simplified to just be a constant. We're going to push that constant out in front as a coefficient. Absolute value can now be dropped, but we're going to balance that information with a plus or minus on the other side. And then we'll let the c absorb that plus or minus. And if you look, this is a fairly clean equation, right? If there was an ordered pair, this is where I want to plug it in because this is going to be fairly easy for me to find that value. Because I'd much rather do my finding for C value here than up here. Okay, so. All right, any questions? So we've seen quite a few variations of these differential equations. So that's good. And then next Tuesday, we're going to get some more practice. I want us to do at least 1 or 2 every day until it just feels like it's just, you know, it's just procedural. And it doesn't feel like complex, doesn't feel like a complex thing anymore. Okay. Any questions? All right. So I think many students feel this is the most difficult thing in this course, and so I understand why, but I'm hoping that through enough practice, it'll just feel like it's not too bad. Okay. All right, let's move to 6.2. Solving differential equation word problems. Okay, so this is going to feel easy compared to the previous section. But the only thing is we got to just be careful, keep track of our numbers, solving for variables. So I have a way to hopefully provide a nice structure for you so you can keep things organized. All right, so a couple of notes here. Direct proportion equation. It's going to come in the form of y is equal to kx. So that will ensure that y and x are both increasing or they're both decreasing. They're going to be having similar relationship in terms of both values are going to be similarly either growing or decreasing. And k is a way to show that relationship between y and x is kind of like a ratio, proportion between the two variables. Okay. And then the inverse proportion, indirect proportion, is going to be where we want to ensure that as one value is increasing to show that there's an inverse relationship. So if one variable is increasing, the other is going to be decreasing. So to ensure that we have one in the numerator and the other in the denominator, with the k again representing that ratio proportion between the two variables. So k is called the constant of proportionality. Okay. And when we read these word problems, we're going to be matching with one of these forms, either the direct proportion form or the inverse proportion form. And what we're going to be doing mostly is going to be direct proportion. And we're just going to have to fill in once we understand that we're dealing with a particular equation, we just have to fill in these two spots. This description is going to tell us what to fill in for this spot, and also tell us what to fill in for this spot. Okay, let's read number 1. If the rate of change of y varies directly with the value of y, find the general equation. So I see rate of change of y, so I know it can't just be y, it's something with y. So that rate of change is going to push it to the derivative territory. So we're going to say that represents y prime. Varies directly, so we know it's going to be in this form of direct proportion, equals k times something else, right? We know it's going to be a direct proportion here, and we're going to fill in what that last variable is. And it says varies directly with the value of y. So just the original variable, no changes there. Y prime equals ky. Okay, so this is a differential equation. But what we're going to see is that we're going to solve this one time through. But once we get to the general equation, we're going to use the general equation over and over again because all these other problems are going to follow the same format. And if we follow the same format, we're just going to skip the calculus and jump to the general equation and then go from there. So let's just focus on solving this for just one time through. Okay, is there a way to rewrite this? Okay, so y prime, we're going to rewrite it. But here's the difference. The difference is that these are word problems with time being the underlying variable. So instead of everything over dx, now it's going to be over dt. So we're going to write it as dy over dt. Okay, so anytime, usually if you see a word problem where you can visualize it, time is going to be involved, and it's going to be always d over dt. So we'll let y prime become dy over dt. I'm already setting myself up for cross multiplying. So cross multiply, dy is equal to okay, we have to shift our perspective a little bit. Usually I know we're expecting x's on the right and y's on the left. Now it's going to be time t on the right and y, or whatever the dependent variable is, on the left. Okay. So we have everything in the right place for the most part. K, let me talk about k for a moment. K is not a variable, it's a constant. So you'll treat k the same way if it was like a 3 or a 5 or 8 or 10. Basically, it's going to stay on the right side. We talked about how we want the left side to be as minimal as possible, and whatever messiness we're going to leave on the right side. So there's only one thing out of place, and what's that? That y. Divide that y over, and it's going to stay in the denominator, right? Stay in the denominator. It does not come up to the numerator. I'm going to push that k out in front, and I'm going to put a 1 here as a reminder when we take the antiderivative. So integral of 1 dt. Variables are separated. The constant k is on the right side. I should be able to take our antiderivative now. So integral of 1 over y just becomes what? Yep, natural log absolute value of y. K is a coefficient, so that's going to stay. It's not going to go anywhere. Okay, what's the integral of 1 dt? Good. dt tells us we're dealing with the time variable. 1 is a constant. We're going to let it rise up to a degree 1. So 1 becomes t, so k times t plus c. We have that constant plus c because of our indefinite integral. Okay, good so far. We want to solve for y. Y is stuck inside the natural log, so raise both sides. E is the base. Drop the e in natural log. Split this up. E to the kt plus c can be broken down as e to the kt times e to the c. We know that e to the c can be replaced with just a big C. Push the c out in front. Drop the absolute value, plus or minus get absorbed into that c. Okay, any questions? So once we recognize that this is the pattern for all the other problems, we're just going to jump directly from here to here without having to go through all this again. Okay, so this is the most common differential equation for these word problems. So if you see that relationship, we're going to jump directly to this, and we can skip the calculus from here on out. Good. Questions? All right, number 2. Let's read the question and see if we can create an equation out of it. The rate of increase of population, we know it's population related, but rate, so I'm going to call that P prime, is proportional. So when you see the word proportional, it's understood it's direct proportion. Okay, so it's going to be the form of y equals kx. So p prime equals k to the population. So p prime is equal to k times p. Right, we're just taking the sentence and putting it into an equation form. Now, is this looking like the same form as?
Yeah.
Okay,
So
so
we just like do p is equal to plus minus.
yeah, that's it. Yep. So we're going to jump all this. It's the same relationship. So instead of y equals ce to the kt, we'll just let this be p is equal to ce to the kt. So from now on, once you see that relationship, we can skip all the calculus. So ultimately, what our goal is, we have all this information, and we're going to be creating a specific model and then using that model to predict a value in the future. So let's read the problem here. If the population in 1930 was 50,000, in 1960 was 75,000, what's the expected population in 1990? So it's a lot of information here. What I like to do is I'm going to create order pairs. Order pairs are a nice way for me to organize information and keep track of what I've used and what I've done. So time is always going to be the independent variable. Think of time t as your x. So my order pair is always going to start off with time. And whatever the other information is, that's my y value. In this case, population. I'll let t represent time, and I'll let p represent population. Okay. So we have a series of information given to us about a certain year, as well as a population that goes along with it. So the first thing is, what's the earliest time value that's provided? 1930. So we're going to let that, in that very first, that earliest time period, we're going to let that be 0. We're going to let that be 0. The reason why is because if we can involve 0 as our order pair, it'll make things easy, cleans up our terms a lot faster. So the earliest time value that we see, we'll let that be 0. So we're going to let 1930 be t equals 0. So that means year 0, population is 50,000. 1960, population is 75,000. So what can we do to represent 1960? Good. So 1930 is year 0. 30 years later is 1960. So 30 years later, 75,000. Right. What's the expected population in 1990? How many years after our 1930? 60. So we'll put 60. But we don't know what that is. So that's what we're going to be using our model to help us find, but not until we have more information about the pattern over the course of the years. So what we're going to do is we're going to always involve 0 first. That's going to be the easiest one. It'll take out one variable quickly and solve for the other. So we're going to use the first order pair, find a specific variable. Once we find that variable, we're going to update the equation, and we're going to move on to the second order pair, plug in, update the equation again, and finally we're going to be ready to make using a model with specific information to find a future population. All right, so start with 0. So 0 gets inserted in for time, and 50,000 gets inserted in for p. All right, what do you notice here? Yeah, e raised to the 0 is just 1, so that goes away. I'm just left with c is equal to 50,000. Okay. Once I have my c value, I'm going to go back to my original equation. I'm going to update that information. So I now have my c value, so I'm going to make some improvements with my general equation. Right, so I've used my first order pair to help me get some information. I'm going to move on to my second order pair. So 30, I'm going to put in for t. 75,000 I'll put in for P, and we can decide what we can get from that. So what variable are we trying to solve for here? Okay, so we want to eventually get to K, but looks like there's a couple of things we can do ahead of time. So I'm going to divide that 50,000 over first. Use your calculator. 75,000 divided by 50,000 reduces to be 1.5. Cleans up nicely. 1.5 is equal to e to the 30k. I want to solve for k, but where is k located? Exponent. It's kind of awkward space for us to solve for k in that exponent. What can I do to make it easier? Yeah, let's use natural log. Anytime we use natural log, we're free to move that exponent. And we want to move that exponent because once you move it down, it'll be a lot easier to work with. So yep, natural log both sides. That 30k can freely move or bring it down in front of the natural log. Natural log of e just becomes 1, so we can just make it go away and solve for k by dividing by 30. Okay, we have our C value that we can update. We have our K value that we're going to update. But one thing I want to point out is hold on to your K value. Okay, don't create the decimal just yet. If you make a decimal here, then your end answer is going to be less accurate. I know that sometimes our answer will be an approximation anyways at the end, but we're going to try to improve our approximation as best as possible, and we're going to hold on to this value. So don't make a decimal out of it. I know it's going to be a little cumbersome to hold on to that, but we're just going to hold on a little bit longer and just make the calculator do all the work for us. Okay, we have our K value, we have our C value. Now let's create our specific equation that we can use to make a prediction on a population. Okay. I have my C value and my K value found. Now I can make my prediction at a specific year. So 60 years, plug 60 in for T, enter all this in, I can find the population. Okay, so 50,000 e to the, I'm just multiplying all the numerators together, 60 times natural log of 1.5, all over 30, but it's all sitting in the numerator slot here. Okay, so there is my predicted population. It looks like I don't have to deal with any decimals, but if there were decimals, you would round to 3 decimal places. Okay. Okay, questions? Okay, all right, let's do one more. Very similar process, just kind of get more comfortable with it. So let's look at number 3 and we'll end there. Okay, no one else needs to see number 2. All right. All right, the rate of decay of radium is proportional to the amount present. Let's create an equation out of this. Rate of decay of radium, we'll let R represent radium. I see rate, I know it's going to be a derivative, so I'll say that's R prime. Is proportional, so I know it's going to be in the form of y equals kx. Everything is going to be in the numerator, so equals k. To the amount present at any time, so the amount of radium present, so that's R. So rate equals K times R. Is that the same relationship as previously? Yeah. So we can jump directly into our equation. So R is equal to CE to the KT. Let's create our information from, let's read the rest of the problem first. If 60 milligrams of radium are present now, and its half-life is 1,690 years, how much radium will be present 100 years from now? Order pair, time always comes first, followed by whatever the other variable is. In this case is radium. So T for time, R for radium. All right, what's the earliest time value that is presented?
0.
Okay, but in reference to the problem.
Oh, well, 1690. Or
So time is now, right? Okay, so it's now being the earliest, and then we're looking into the future. So we'll let now be t equals 0. So right now, there are 60 milligrams of radium. Half-life is 1,690 years. How would you create an order pair out of that information?
so 30 is or 1690 and 30.
Good, right? So we want to put the time information first. So that's 1,690 years from now. There's going to be half the amount of radium remaining. So 60 is going to turn into 30. How much radium will be present 100 years from now? So 100 followed by unknown. One piece at a time, we'll take our easiest order pair. That 0 is going to help us find a value for us, or it's going to eliminate a variable for us. Very similar process. E goes away, K goes away, I'm just left with C. Update our equation once you have certain information about it. Let's use the second order pair to help us find more information. 30 goes in for R, 1690 goes in for T. I want to get to K, but before I can get to K, I want to get that E to the K by itself. Let's move that 60 over to the left side. Reduce it to be 1/2. I'm going to use 0.5. What's next? Yeah, let's involve natural log on both sides. Bring that 1690K down. Natural log of E goes away nicely. Divide both sides by 1690. we have our K value. Okay, let's create our specific equation now that we have information, full information. Hold on to your K value. Don't create a decimal out of it yet. Okay, so we're ready, right? 100 goes in for T, and whatever this mess gives us is going to be the amount of radium 100 years from now. Okay, we're probably expecting this to be a pretty large value, right? Since it's going to take over 1,000 years to get to 30, so probably be a lot closer to 60 than it will be to 30. Oh, I'm just enter it in. So 60 times e raised to the natural log of 0.5 times, oops, I forgot to put 100 there. Okay, what you get for R? Yeah, let's round it to 3 decimal places here. Yeah, 57.589. We've gotten the best approximation we can because we held on to our K value and we didn't let a decimal in yet. So we're saving, having that middle point be as accurate as possible so we can get that 57.589. Okay, milligrams. Okay, questions? Okay, so on Tuesday, we're gonna finish up with 4. We'll do a practice 1 or 2 solving differential equations, and then we have another topic, which is slope fields. Okay. All right, thanks everyone. Hope you guys have a nice holiday weekend. See you Tuesday.
Have a nice weekend, Mr. Yang.
You too, have a good weekend. Thank you.